Hello everybody, welcome back to Damage Control Assistant Senior Enlisted Curriculum. This is going to be Lesson 2 in Chapter 5, where I'm going to derive that formula that we saw in the last video for the free surface effect. I'm Lieutenant Timothy Mueller, and let's get going. Alright, now to start all this off, we have to take a look at a diagram and see exactly what we're up against. So here on this diagram on the left, we have a ship, all this right here. It has an initial center of gravity here, which moves vertically to G1. This is what we're ultimately trying to find. However, in this step, we're trying to find this right here. This lowercase b is going to be the center of gravity of the tank contents originally. This B1 is going to be the center of gravity of the tank contents at some inclination, theta. M is going to be the metacenter of this center of gravity moving around. G, lowercase g here, and lowercase g1 is the center of gravity of those wedges that we lose on the left side and gain on the right side. So the center of gravity of these triangles moves from here to there. W, L is the original waterline. W1, L1 is that new waterline that we have. And theta which is the overall inclination of the ship here, is also this angle right here, BMB1, and it's also this angle here, LSL1. All right, to start off this video, here's a list of all the variables that I'm going to use in this derivation of the free surface effect. Take a look at this. I would suggest do a print screen and open up some program that allows you to copy or that allows you to paste that list and have it on the right side of your screen or the left, whichever you prefer, so that you can reference this while I'm doing this derivation. So here you go. All right, so the first things first is we have to start seeing the moment that's created by the movement of all this liquid. Remember, this is an actual tank, so it's in 3 dimensions. We have a 2-dimensional transverse perspective here, but also imagine it coming out or going into the board. It has some sort of a longitudinal length. So we have to find how much is this moment from the contents going from here to here. So it goes from B to B1. So you have to take that volume that we have inside the tank, you have to multiply it by the distance B1. So all this contents is essentially going from this center of gravity to this center of gravity. Now we take that bulk measurement and we chop it up into these triangles here. We have, like I mentioned, WSW1 and then LSL1. How far is that moment that's shifted? So if we take E being the area of WSW1, which is the same as LSL1. So just the area of one of these triangles. And then we multiply it by G1. And G1 is this distance here, the distance between the center of gravities, times the integral from 0 to z, dz. Z is just the axis that goes into or out of the board. If you have a constant width of the tank, then this this integral would just boil down to that length, L. However, we're going to take as many assumptions out of this equation as possible and then see how it all works at the very end. Now, the free surface effect has a huge impact on the initial stability of the ship. Initial stability of the ship means small angles, which means we can start linearizing. When we linearize, we're going to take sine of theta equals theta, like we saw in our sine and cosine correction videos. Then we're also going to talk about cosine. When we do a Taylor expansion on cosine, the linear term is just 1. So we can take sine theta equals theta, cosine theta equals 1, and start to boil this diagram down to things that we can actually use much more readily. Now GS equals G1S, and we know that. The center of gravity moves here to here, and it kind of pivots off of this point here, S. Now we want to find this distance here, the horizontal distance, S to G1, which is the same as G to S1. Now if we know that this here, SG1, is the hypotenuse, then we know that this S and then this point right here to make this right triangle is going to be SG1 times the cosine of theta. But if we have cosine of theta equals 1, then we know that this length here, G1S, equals this right here, S to this point, assuming linearization is accurate, which means that cosine theta equals 1. This center of gravity, we know from, it was actually in lesson 2 of chapter 0, we talked about center of buoyancy, but more specifically centroids. We know that the centroid of this wedge is also going to be in the same spot of the center of gravity, assuming it's homogeneous. So now we know that our center of gravity is going to be 2/3 away from the pointy end, or 1/3 from the big end. If this length is the same as this length, that means that our imaginary point right here is at 2/3 of the length of the triangle, which is H. So GS equals G1S, which equals 2/3 H. Next up, this E being the area of these small triangles, equals 1/2 of the base times the height. Now if we take 1/2 of the base, so let's work with LSL1, 1/2 of the base is H divided by 2, or 1/2 of H. Now this height, we know that that is the hypotenuse times the sine of theta. Now if we assume that everything's correct with linearization, then we know that our hypotenuse here and H are going to be the same. So this side here is going to be H, which equals this equals this, by assumption, times the sine of theta. But sine of theta equals theta. So that all boils down to H theta. So the area of this triangle is 1/2 H times H theta. Now that we've made all of our assumptions for linearization, let's go back to this very first equation that we mentioned, work on one side, work on the other side, and see what we come up with. So let's work on the right side for now. We have E, the area of this triangle, times GG1, which is the overall distance here, times the integral from 0 to some point in or out of the board, dz. So let's work with our linearizations. E equals 1/2 H times H theta. So we're going to put 1/2 H times H theta right there. Then we know GG1. Well, we know that GG1 is just GS plus G1S. So if we double what we had here, GS plus G1S equals 2/3 H plus 2/3 H, which equals 4/3 H, right there. So now we have E times GG1, then we just keep that integral. Now we just combine all of our like terms and make this a little bit easier to handle. We have 1/2 of 4/3, that's going to give us 2/3. H, and H right there is H cubed. We have 1 theta left over, then that integral right there. Now we haven't made any assumptions about H or the actual equation or actual behavior of it, so I'm going to keep it outside the integral for now. But if there was some variation in H, then H would go inside. But we can move it inside and out because we haven't performed that integration yet. All right, that was the right side of that equation. Now we got to work on the left side of the equation. V times B1. V is the volume of the liquid that's inside, and then B1 was the distance from B to B1. So it's the overall moment of all that liquid moving over. So V times BB1 equals V times BM sine theta. Now in this step, BM is exactly what we're looking for. So we're starting to move in the right direction. Now I'm saying that BB1 equals BM sine theta is right here. We have this triangle here. Assuming it's very close to a right triangle, we know that BM is our hypotenuse, and we're trying to find this BB1, which is this distance right here. So, just by using trigonometry, we know that BB1 is BM sine theta. But using our linearization, we know that sine theta equals theta. So let's rewrite this as this right here. V times BM theta. Then that's about as simple as we can make it. Now we're going to take this, which was originally stated as this on the left side, equals this right here, which we'd already calculated or we'd already manipulated to be this, which is just this rewritten. So this right here that you see, v bm theta equals 2/3 h cubed theta with the integral, is just this up here, but just rewritten and algebraically manipulated. Now, if you've taken any engineering classes and you've seen the last video, you should see right away where I'm going with this. Now, rewriting this equation here to there to here, now we're trying to solve for Bm. We have this theta on both sides, so we can just cross it out. The thetas cancel each other. So now our behavior doesn't matter on theta when we're talking about small angles, where we assume that our linearization is accurate. Now we're just trying to solve for Bm, which means that we just divide both sides by this V, the volume of the contents of the tank, and then we're all set. Like I mentioned, for algebra, we're going to keep that h outside of the integral, but if there was variation in h along that z-axis, the axis of integration, it would have to stay inside. Now we have Bm equals integral from 0 to z of 2/3 h cubed dz divided by this little v being the volume of liquid inside the tank. This right here, this integral, is the definition of the moment of inertia of a plane along an axis right on its center of gravity. Why did we do this step? It seems like a lot of complex manipulation and a little bit of trickery when it comes to linearization to do. It doesn't really seem like anything. Well, think back to the actual equation for center of gravity. Center of gravity has big M times big R equals just the sum of all the moments. If we're trying to find how far a center of gravity moves, however, we just take the additional moment or removed moment and divide by the total mass of the system. By using this model here, by saying that all of this mass and all of this weight down below can be remodeled as having a center of gravity up here, all we have to do is just treat this as a weight shift, and then we see how far our center of gravity moves. So let's get into that right now. We've already seen Bm. We now know Bm. That's I over V. How does this affect that? All right, so now we've solved for Bm, basically that virtual rise in the center of gravity of the tank itself. Now we have to find the virtual rise in the center of gravity of the ship itself. This right here. So I've just rewritten what we've already solved from the last part of the video. Bm equals I over V. I being the moment of inertia of that free surface, V being the volume of the contents of the tank. Now, let's just treat this as a weight shift. So pretending we're shifting this weight from B, the original center of gravity of the tank, up to M. We get delta F, which is the final displacement of the ship, entirety, G1 being the distance from G0 or G0 to G1, then Bm, which is the distance we've virtually moved our weight, and then W being that weight of the water inside the tank, or whatever the contents of the tank is. Now let's do some algebra. We're going to take this final displacement over to the other side, so we get G1 equals Bm, which I've just rewritten as I over V, times W, the weight of the contents of the tank, divided by that final displacement. Now we take that V down to the bottom. I've done no manipulation here. I've just rewritten it. So we got I times W equals V times the final displacement. Now this V is the volume of the tank and this W is the weight of the tank. We know how to convert from weight to volume. All we have to do is use the specific volume. So now if we take this W and we say the weight of the contents of the tank, which we talked about in chapter 0, lesson 3, equals the volume that I have of the tank divided by the specific volume. So take that, weight equals V divided by specific volume, plug that into the equation here for W, we get Gg1, the movement of the center of gravity, equals I times W, which is now V divided by specific volume, divided by the denominator we had here. But now we see there's a V up top and there's a V down low. Cross the V's out, and now we're starting to get somewhere. We have I divided by specific volume times final displacement. And that's pretty much as close as you can, that's as simple as you can make this formula. But when you're in DK school, we're only going to be talking about rectangular tanks. Typically, unless you're using some computer software, you're going to be talking about rectangular tanks. It just makes everything a lot easier. So now, knowing that or assuming that we're dealing with a rectangular tank, how do we make this even simpler and get to that formula that we've seen before? Now, assuming that there's no change in H, so the derivative equals 0. We've used calculus before, so I'm going to assume you know a little bit. Assuming that dH equals 0 along the entire axis of integration, then we just simplify this, the integral from 0 to 6 dz equals L. L being that longitudinal length of the compartment of that tank. So if we know that I is now 2/3 h cubed, since there's no deviation in h is constant, we can bring that out of the integral. H cubed times L. If we know that h is just half of b, or capital B being the entire width of that compartment, and h just being half of it, we take that, now we stick it into the formula for I. Now we have 2/3 times h cubed. If h is b over 2, then we have b cubed over 8, 8 being 2 cubed, times L. Now if we have 8 equals 2 times 4, then that 2 on the top here is going to cancel with that 2, making this a 4. Take that 4 times the 3, that's going to give us 12. Right there. We have b cubed times L. And now this is the exciting part. You put this back into the formula. We originally had I divided by specific volume over delta F. Now we have GG1, which is the movement of the center of gravity of the ship. That's not kg, it's not this distance. It's just the distance from G0 to G1. That movement equals b cubed, assuming we're working with rectangular compartments, b cubed, b being the overall width of that compartment, times L, L being the longitudinal length of the compartment, divided by 12, which just came from the physics of moment of inertia, times the specific volume of whatever the contents inside the tank are. For diesel fuel, 43 cubic feet per long ton, and usually in D case we're going to be using salt water being 35 cubic feet per long ton, then times the final displacement of the ship. And that is how you derive the equation for the free surface effect. Now, when you come to this school, you are not expected in any way, shape, or form to be able to derive the formulas that you see on the equation sheet that we give to you for your exam, final exam, and everything else. However, I know there are some people that really just want to see exactly how things come to be. When you take a look at this equation, it doesn't really make sense where the 12 comes from. Why do we have b cubed? There's a lot of things that can raise questions. So this hopefully cleared up a lot of those questions that you have. Anything else, you can just look on YouTube or any other video or lesson that you find online when it comes to moment of inertia or free surface effect. Now, on the next video, we're going to go through some examples of the free surface effect in different perspectives and see exactly how we can apply free surface effect to an overall vessel. But that's going to be for the next video. Till then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.